Ooh, all right. Good morning. Good morning. Good afternoon. Good evening, wherever you are. Can you guys hear me? See me? Am I there? Am I here? Am I somewhere else? Mhm. Who knows? um, all right. Good morning. How is everybody doing? I see a lot of familiar faces. Uh, oh, I see Watch Tech and Hari Prasad. They are here. Hi, how are you guys doing? Uh, can we can we give them a round of applause? They have been really helpful. They've been working with me on cleaning up the files and making them more legible and grouping them and putting text and so that we can publish them on GitHub and making them available for everybody. So can we please give them like an applause? This is WatchTech and where are you? WatchTech and Hari Prasad. Yes, they've been helping a lot. They've been super helpful contributing to the project. So thanks a lot for them to them. Um, I see people from India, from Lithuania, from Brazil, from here, from the US. I'm always surprised to see you guys all from everywhere that you're coming and to have this like really um, wide array of people and cultures. I think it's really interesting. I think it's the power of the internet and the power that we of the times that we live in. It's I don't know where you guys are. People from Mexico. Um, uh, I don't know where you guys are, but and what the weather is like there, but it's really sucky and really bad weather here today in Boston. So I hope the connection doesn't cut. I had a lot of internet problems yesterday, so if the connection drops, I'm sorry. I'm not sure what I can do about that. I'm recording this anyway, so the video will end up somewhere online correctly. But yeah, so all right, Singapore. Oh, I had a friend. I have a really good friend who just moved out of Singapore after 5 years. He finished his PhD and he's in London now. Well, he's in Malta right now. Anyway, what are we doing today? Well, I want to spend some time saying hello to everyone. If you guys can say hi and say where you're coming from, where you're calling in from, and just like what would you like to see for this channel and for these tutorials. I always read the chat after the fact. So even if I'm not responding live right now because I'm trying to pay attention to a lot of other things that are going on, I always read the chat and I read your comments. So, so yeah, so feel free to post your ideas and where would you like to see this going. Where this is going right now, I have an announcement. I have finalized deciding and implementing and fully setting up the new channel. As I mentioned before in previous streams, I didn't feel very comfortable keeping the streams in my personal YouTube channel just because I would like to make the streamings and this community its own thing and open it up to other participants and other people recording tutorials at some point in the future. So I thought it would be a good idea to migrate everything to its own channel with its own name and its own thing. And we have finally decided on that. I did an announcement last week about this, but it's final now. So the new channel is going to be called Parametric Camp. And this comes from an initiative that my brother Fernando and I did in 2011 and in 2012. We did travel around Europe and around Spain, and we did a lot of like in-person workshops on parametric design, computational design, and all these things. We stopped doing it in 2013, but we already had the website, we had the name, we had a lot of work done. So we thought that just perhaps like picking it up again and bringing it back to life could be a good idea. And I kind of like the name. We were going to do parametric campus, but it turns out that it has 16 letters, which is terrible for Twitter because you can only have 15 characters for Twitter usernames. So we stuck with parametric camp. So what I'm going to do is I'm going to paste here. Where is the link? I'm going to paste here on the chat. I'm going to paste the link to the new channel. So if you guys fancy, please come over and subscribe. We already have a channel, and we have social. We have Instagram. We have Twitter. We have GitHub account. We have already started posting the videos that we recorded 4 weeks ago. Yeah, we've been working on the background to make this happen. But we've been posting the videos that we recorded. We have edited them. We have chopped them. Now they're more concrete. They're like there's not so much like back and forth from me, which could be or not be boring. We also have links here to where you can download the files, where you can see the second, the third part, the original recording, social, etc. And as you can see, I like math and I like cooking from my suggestions. so, so yeah. and and so oh, I see 7 more subscribers just right now. I'm going to keep reminding everybody of the subscription over the course of this video. So if I'm a little annoying, don't apologize me. But I wanna start transitioning everyone as soon as possible to the new channel so that we can start streaming always from there. What I plan on doing is I plan on maintaining live streams from this channel, from my channel, because it has a bigger outreach right now. But I plan on transitioning to the new channel. So all the videos, all the edited videos will be posted only on the new channel. And starting probably next week, I will start streaming in the mornings from my channel. Maybe I will do tutorials that are like in line with what we have been doing. So our algorithmic modeling, challenges, cool stuff, C#, etc. But probably in the afternoons, I will start streaming directly from the Parametric Camp channel. And I want to start recording like a series of like Grasshopper tutorials and C# tutorials so that they become more, so that we turn them into a learning resource and a teaching playlist. So, so there's going to be like at least a month of overlap between the two channels until we feel that we can fully transition and just concentrate on Parametric Camp. So how do you guys like the name? Honestly, I mean, I've I've put so much work these 2 weeks in making this happen that I don't think I'm gonna change it. But if you hate it a lot, you're also welcome to say on the chat. I think it's nice and catchy. Parametric Camp. It's like, oh, let's go camping and like spend a week doing stuff. That was the original intent. Maybe at some point when things get back to normal, we can bring back in-person events and start throwing like flying to places and have like online physical workshops. Maybe we can also do online seminars. What is a little less of me talking and more of like us, all of us talking together. It is my hope to build an actual community around this project, and make other people participate and bring their ideas. I have no idea how that would look like yet, but hopefully sometime soon. Now, I would like to say that I have been very overwhelmed by the response that the last stream had, where we were doing Grasshopper Sharp. So where we were taking normal regular Grasshopper components and then mimicking their functionality in C#. I've gotten a lot of emails, a lot of Instagram messages, a lot of like people trying to connect, people showing me their files. It's been really, really nice. Baba went ahead and like she sent me like a bunch of images of how she took all the components that we did in the previous stream, and she also added her Python version, her Python implementation, which I think is super cool. I would like to expand the project also to include Python at some point in the future. And there, I wanna highlight this Chino 89. sent me a link to his GitHub repo, where he also wrote Python implementations of the exercise that we did last week. I thought it was really cool. Actually, a bunch of people, a bunch of people reached out to me because they wanted to contribute to the Grasshopper Sharp project, and I already started like an email where we're talking about those, and there's been some contributions. So it's been a really interesting thing. I want to thank everybody who've manifested their interest in making this happen. And I think it's great. I'm very happy about this. So maybe if actually more people jump in and we code together, maybe we can actually push and publish the first alpha, the first public version, much sooner than I thought. That would be amazing. Um, so so yeah, and I also want to give a shout out to, I forget his or her name, but somebody, this, I think it's a gentleman from Turkey, Mert. Mert sent me this really cool video. So he basically took some tutorials that I have on my channel where I connect, where I show how to use Runway ML, which is a machine learning framework for artists, for visual artists, and he connected it to a project that he was doing on a course that he was taking. So he basically rendered this video, this 3D scene with 3D Max, but then he passed the video through a style transfer neural network in Runway ML so that it gave it this texture and this quality of, I think it was Cezanne, the main painter, but he also did this like puppet scenes where like the actual frame is styled in a different painter. I don't know. I thought it was a really cool project. It doesn't really have much to do with what we've been talking about so far in the channel, but I'm super into machine learning these days. So I hope once we cover, I want to cover first like the basics, like Grasshopper, C Sharp, Python. Like let's learn how to code. Let's like create good content about that. And once we have that under control, then we can move on to higher things such as machine learning and robotics and that kind of stuff. I will definitely do like a series on robotics at some point soon. But I thought this was a really good project that I wanted to show and share with the people. Let me take a quick look at the chat. Camping with the parameters. Yeah. Yeah, I'm also mind blown. Yes. All right. Um, okay. So, what are we doing today? Today we are continuing with the work that we started in the last stream. So we will be, because there were a lot of components that I didn't have time to get to. So I would like to continue with that work, and I would like to do more Grasshopper Sharp. I would like to take more standard components, more out of the box, more vanilla Grasshopper components, and mimic them in C Sharp. Last week was perhaps a bit more beginner, so I went over the basics of like the C Sharp scripting component, etc., etc. Today, what I would like to do is like I would like to move on to perhaps more advanced topics. Then maybe they're not going to be so advanced; they're going to be intermediate. I would like to do more stuff with geometry, which we didn't really do much last week. Perhaps we will touch upon data trees, but most importantly, I also want to open it up to you guys. So I have a list here somewhere of the components that I want to go over. And I started a little earlier today because I want to have enough time to get them together. But I would like to invite you to think about, while we're doing this, which components would you like me to try to replicate? I don't know if that's a good or a bad idea because if I don't really know how to do it, it may actually take us some time to figure that out. But apparently you like that. Apparently you like sitting down and like watch me like freak out, like, oh, how do you do this? Like, where do you trying things out and failing? So if that's your taste, then I'm cool with that. I'm perfectly cool with that. Um, Now, so I would like to invite you to think about or like take a look at the components that you use very often, And by the end of the stream, so when I'm done with, like, I have a list of like 5 or 6 that I want to go over. So when I'm done with those, I will open it up here to suggestions, and then we can have a small conversation about which components would you like to see, and maybe I can suggest like some are more difficult, some require like more unpacking. So we can do that. I see, for example, a suggestion for mass addition. Mass addition is actually super easy to do. So we can probably take a look at that. Now, is there anything else that I want to go over? No, I don't have anything more in my notes. So we can probably get started. All right. So, um, okay. So I'm gonna go here, and I'm gonna do. Should I pull up last week's video? Should I pull up last week's? Um, last week's files. It doesn't make any sense to open that. Okay, so maybe I can do that. This was last week. Maybe we can just have it here for the sake of reference. It probably doesn't hurt. I can probably just turn everything off. Here, right, and here, and here, and here, and where is that point coming from? Okay, we can probably just keep it there. Random reduce, evaluate curve. I'm going to do evaluate curve today. Solid intersections and unions. Surface and curves analysis. I will do a little bit of that. The basics functionality of Galapagos. That is a little more involved that we can probably reach today. So I don't think we will get to cover that today. But it's actually, I mean, doing a form of simple Galapagos, so doing like an optimization process, that's actually not very difficult to do. I mean, the difficult part with Galapagos is like the UI and the genome and blah blah blah. But in actually writing a component that does like a bit of like a small control heuristic search is actually not that hard, and it's an interesting exercise. So maybe we could do that. I'm gonna write that down. That sounds interesting. Like a simulated annealing exercise. That could be good. Who said that? Karan. That could be an interesting topic for an actual stream. So thanks a lot for that. I'm gonna give it some thought. Huh. All right. Yeah. Okay. All right. So I'm going to do as usual. I'm going to start. What do I have here on the list? I want to go over. So last week we did. What did we do? We did addition, list items, series, range, construct point, deconstruct points, and vector algebra, and then lines. Okay, so I think I have here on my list, what I want to go over today is I want to create an interpolated curve. So I want to have like a bunch of points, and I want to create a curve over them. I would like to evaluate a curve. So having a curve, what can we find? What about that curve? Given a parameter, can we find or the perpendicular tangent, the perpendicular vector, the tangent vector, the perpendicular plane, the point that is on that parameter. What we can divide the curve in equal segments and perpendicular planes. I would like to loft a surface, and then I would like to evaluate a surface. So given UV coordinates of that surface, get the normal vector, get the perpendicular plane, and that kind of stuff. Somebody suggested mass addition. We may want to take a look at that, but I'll get back to that by the end of the stream. So again, think about which components would you like to see. And by the end of when I finish with the ones that I want to cover, then we can have a small conversation, and then I can go back and do one or two of the ones that might be easier to do. Somebody's asking for forward and inverse kinematics. That is actually an amazing topic that I do want to cover at some point, but I do want to do it more consistently. I teach a lot of robotics, so I actually want to make a playlist with like basic principles of robotics, and maybe we can do like our own robot here on Grasshopper, so we can like a robot with like 3 joints and do like we can use Galapagos to do inverse kinematics. That's actually a really cool exercise. It's not the most optimal, but it is a good exercise, a fun one. So maybe we can do that, but I want to do that more consistently. So it's gonna take some time to get there. Okay. All right. So I'm going to, as usual, I will leave the introduction to the end of the I'm going to leave this introduction to the end of I will record that by the end. I want to remind everybody who has just joined that we are moving to a new channel. We're moving to a new channel called Parametric Camp. So if you want to subscribe and stay up to date, we will be transitioning very soon. So I'm posting on the channel the link to the new YouTube channel. Okay. All right. So let's get done. Should I record the videos with like a watermark or something with the logo? I think that's probably too much. Okay. So let's start with interpolated curve. Which one is that, by the way? It's here. Interpolate, create an interpolated curve through a set. Oh well, so let me just do like I typically do. So I'm just going to place here like a bunch of points, for example, and then I'm going to pick them up. I'm going to pick them up, and then I'm going to throw them in here. And this is the degree, this is the periodic curve, and this is the knot spacing. Okay. Okay. So, and we have the curve, we have the length, and we have the domain of the curve. Okay, this is going to be interesting. So, for example, I'm going to paste a 3 here for the degree, whether if the curve is periodic or not. So that's going to be a toggle. And then the knot spacing is going to be chord spacing. So number 2, I'm not going to bother much with that input actually, because it's a little complicated to explain. So we're not going to cover that today. And then the curve is going to be this, which gives me the actual curve, it gives me the length, and it gives me the domain of the curve. All right. Okay, and I'm going to move this down here. And I'm also going to, I'm going to do this already. So this would be D is going to be, and then we have P periodic, well, if it's periodic or not, and with the K value. And then here we have C, that's the curve. And then we have 2 outputs. We have L, which is the length, and then we have D, which is the domain out. Okay, and I'm going to toggle the parameters. I'm going to toggle them as part of the video. Okay. All right, shall we? Are we ready for this? Are you guys ready? I'm never ready for this, so I don't know what I'm doing with my life. Okay, so recording mode. Okay, I am the logo. Sarab, seriously. Okay. All right, let's do this. Focus. Okay, also I'm going to pull up, I think it's going to be good. I'm going to pull up RhinoCommon Interpolated curve. I think this will be useful to to explain what I'm going to do. Yes. Should I show this right away, or should I actually show how I got here? I'm going to, yes, I'm going to do it from here so that I can show how I would get to that help screen. Okay. Okay. Good. Okay. All right. Recording mode. The first component that we're going to deserialize or reverse engineer or like try to mimic is going to be the interpolated curve component. This curve basically takes a list of points. It takes some parameters about the curve, so the degree. It takes whether if it's periodic or not, and periodic means whether if it's closed or whether if it's open. And it takes some parameters about the knot information of that curve that we're not really going to mimic in this particular tutorial. So what you can see is that I already created a bunch of points in Rhino. I loaded them in here with in Grasshopper. I set up parameters for the degree and the periodicity of the curve. And as you can see, the result of the component is this smooth curve that goes through the components, but also the length and the domain of the curve. I'm going to replicate all of these inputs and all these outputs. So I already have a C# scripting component that I have dropped here. I have copied all the inputs, all the outputs, and very strong reminder, remember that you need to right click on the inputs and then set them whether if you want them to be an input of the type. So for example, V is going to be 0.3D, D is going to be an integer because the degree has to be. Can the degree have a decimal part? I'm not sure it can, but so I'm going to leave it as an integer for the time being. And then Boolean is going to be bool, and then K is also going to be an integer. Now, the one thing that I need to remember is that this component takes a list of points, which means that if I left V vertices with item access, the component will not work correctly because the component will try to create one curve with each one of the items that has been provided to it. So each one of the points that has been plugged in here. So that's why we need to change the access level of the V parameter, the vertices, to list, so that the component works with the full list, so we can see the full list of points and then create a curve through them. All right? And then, but for the other, D, P, and K, we can leave those as item access. I'm going to plug that in here, in here, in here, and then I'm going to just plug in an out component, and then I think at this point we're ready to start writing our code here. All right, but before we do that, I would like to figure out how can we create an interpolated curve. And for that, I think what I'm going to do is I'm going to go to the RhinoCommon documentation, which is probably going to be the best way to find how from the Rhino geometry kernel I can create such a curve. Remember that if you go to the RhinoCommon documentation, the main namespace that you want to be using is the Rhino geometry one, which is the one that contains all the geometry goodness. And because I want to create an interpolated curve, I'm going to just search something here like curve interpolate or something like that. Okay, and I'm going to see what comes up. I see that a lot of things come up. This is really good, and curve.create interpolated curve kind of sounds like something that I want. So I'm going to click here, and what I see is that this is the documentation page of the function that creates the interpolated curve. It is very important that we check these because the RhinoCommon documentation will give us a lot of information about how to use this method, what kind of information do we need to feed in, etc., etc. So it's a very useful one. I'm going to backtrack a little, and just because I can see that the create interpolated curve method belongs to the curve class, I'm going to go to the curve class, so here, you know? And I can see that the curve class in RhinoCommon has a lot of stuff. So it has constructors, it has a lot of really interesting properties. So the degree of a curve, the domain of a curve, we're so going to use this for this component. It also has the point at the start, this point at the end, whether if the curve is periodic or not. So all of these are values that we can get from the curve. And then it has a lot of methods. It has, for example, find the closest point to some other point, whether if it contains a point or not, methods to create curves. And you can see that all of these ones that have the orange S, all of those are static methods. I will explain what that means in a second. Fillets, you can tween, you can find the curvature at some point. We will definitely use this down the road today in other components, but it has a lot of goodness. So the curve class is very complex. It has a lot of stuff, and it's very interesting. I think we have used I can see that we have used isPlanar somewhere in the past. So so it has a lot of stuff. So if you're learning C# in Grasshopper, it's probably worth the time sitting down and like just doing like a quick read over what is available in certain classes so that you can understand what kind of things you can do with the geometry that RhinoCommon provides you. I'm going to go back to create interpolated curve. So you can see here that I have 3 static methods with the same name, each one of them taking different inputs. So one of them takes point 3D and an integer, another one takes point 3D integer and curve not style, and this one takes blah 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 and then 2 more vectors. I think the one that I want to use is this one because it feels like it's the one that matches the inputs most closely, because if I click here you can see that this method, in order to create a curve, takes a list of points. IEnumerable is an interface that means that this is a collection of point 3D objects. Then it takes an integer, which is the degree of that curve. And remember, NURBS curves normally are degree 3, but you can go all the way from degree 1, which is basically straight lines and straight segments, to degree 5, which is like a very smooth curve, and higher and higher. It's just that the higher the degree, the more computation it takes to calculate the curve, and you don't really see much more benefit. And then the curve not styles, which specifies whether if the curve should be periodic or not. So that's going to be super useful for us here. And also, one thing that I would like to note is that this method is static. What that means is that whenever I call it, I need to call it from the base class. So I cannot call it from an instance of a curve. Let me explain in the component what this means. What I'm going to do here is I'm going to go back to my component and I'm going to say I'm going to create a curve object, which I'm going to call C. And then what I mean by static is that in order to create this curve, I need to access the create curve, the interpolated curve method from the base class, from the curve class. And as you can see here, as I press dot, all the static methods show up. I have a lot of methods to create different kinds of curves. And I think the one that I want to use is this one, create interpolated curve. As I open my parentheses, you can see that I can go and navigate between the 3 overloads, so the 3 kinds of inputs that I can give it, so the list of points, the degree, and the knots, or even I could work with the starting and the ending vectors, which I'm not going to do right now because it's not part of what the component does. So I think I want to stick to this one, where I need to pass first a list of points, so that is V, that is what's coming from the input. I need to give it the degree, which is V, that was also what's coming from the input. And then I also needed to give it the curve not style knots. What is this? I'm not sure, I haven't done this ever, but I'm going to say that okay, I'm going to go back to the documentation. Since this input is of the type curve not style, what I'm thinking is probably this is some kind of enum that gives me, that given some numbers, give me the possibility of choosing what kind of periodicity and how the knots are handled in this curve. So if I have no idea what that is, I can go to the documentation and you can see that here on the parameters, I can click on rhino.geometry.curve.knot_style, which takes me to here. So what this is telling me is that curve knot style is an enum that has 6 different potential values. All of them being whether if this is uniform, a chord square root. So those are how the knots are handled by the curve. And then it has the same 3, but on a periodic way. So with the same knot distribution, but making the curve close to each other. So what it looks like is that I may actually have to do some pre-processing in order to find out which exactly is the knot that I want to use. So let me go back to Rhino and do that. I'm going to leave this not working for the moment. I'm going to copy paste here this value. So I think by default is 2 here. All right, I'm going to paste that in here. This is an integer. Okay, and if you remember, the input here says that you can see that it says 0 is uniform, 1 is chord, and 2 is square chord. So what I would like to do is I would basically like to implement a rule where reading at the knot style and reading on whether if the curve is periodic or not, I choose the right value here. Okay, and how am I going to do that? Basically, I'm going to take the value of the chord, which you can see that is the same as in Grasshopper. 0 is uniform, 1 is chord, and 2 is chord square root. And if the curve needs to be periodic, then I'm going to add the value of 3 to these numbers so that I turn them into these numbers. Very simple. So let me pre-calculate that. So I'm going to say knot style equals whatever the user is giving me as k. Okay, and if p equals true, if the input of periodic equals true, or I can simplify this by just saying this, then knot style is going to be, I'm going to increment it by 3 units. So now that I have that, I actually need to create a knot style enum. So curve knot style, is that correct? Curve knot style, yes, curve knot style. Style is going to be equal to knot style. Is that correct? Does that work? And then here, I'm just going to input that, and then the curve is going to be, the curve that I output is going to be C. These are going to be the outputs. Is this going to work? Let me check. It cannot implicitly convert from integer to knot style. So I need to find a way to convert this, which is an integer, to the actual curve knot style. I think I can do that by casting this. Am I correct? I think I can do such a thing. I can just cast the integer into here. So what have I done? What I've done here is using this parenthesis in front of the value and specifying the type. What I have done is I have converted an integer to something of the type curve knot style. Another way to go about this could have been curve knot style, and then if I use the dot notation, you can see that I get a breakdown of all the options that I can feed in here. The problem is that I cannot choose them by their integer value, which kind of sucks. So I will need to write like a very long if else. If knot style is 0, then choose chord. If knot style is 1, then choose blah blah blah, you know. So it would take a little bit of time. So I think this is just easier to do. Okay. So with that, if I click here, I should have my planar curve, and if I turn this off, you can see that indeed I get the exact same curve that I created. Now, what about length and what about the domain? Well, that's actually very easy to do as well. So here, once that I have the curve, what I can do is I can, for example, I can say curve length is probably C, which is the curve that I just calculated, dot, and there's probably something that computes the length of this curve. So what am I what am I going to do? I need to find this. So here, get length. This is a component that I open parentheses, and it has a bunch of overloads. So I can just get the length with a very small tolerance. I can specify which tolerance I want for calculating the length. I can calculate the length of a subdomain, just a chunk of this curve, and I can combine those before. So I'm just going to use this method. Now you may ask, why is it a method? Why do I have to get length? And why not something similar to other scenarios where I just ask for the length property? Well, the thing with NURBS curves is that because they're mathematical entities, it actually takes, depending on the NURBS and the number of the degree value, etc., etc., it actually takes some computation to figure out the length of that curve. It's not as easy as calculating the length of a vector, for example. So because it takes some CPU power to do that, it's something that objects don't have as information by default unless you ask them to give you that information. So that's why probably they chose to use a method here to get the length instead of just a property. So let's see if that works. So if I output L equals curve length and I run that out, I can see that the length is the same, so we're good. And then the last thing that I need to do is I need to figure out the domain of the curve. Remember that the domain of a NURBS curve is the range between which the parameter value goes. And the parameter is the parameter, you can think of it as like some form of like relative length along the curve. Is not exactly that, but I actually, if you want to learn more about that, you can probably check my Harvard lecture, my Introduction to Computational Design course on YouTube, and I have like some videos that explain NURBS curves quite in detail. So remember that the domain in RhinoCommon terms is called an interval. So I'm going to say that this is going to be C dot, and there's probably something, yes, gets the domain of the curve. So I'm going to take the domain and I'm going to spit that out through d out dot d. All right, and as I do this, no, sorry, this is not d, it's dom. All right, so yeah, so there we go. Now we have the component that takes a list of points, degree, periodic, and the knot style, and gives me all the information. It gives me the curve and gives me all that information for that curve. Okay, I think this was really useful because it's very basic and very interesting to learn about this. Nice. Let's move on to the next one. Okay. Was this too much? Was it a lot? I think this is where it starts getting interesting. Don't you guys think so? Because it's geometry, but it's also code. That's exactly what I like leaving myself. Okay, I need to take a small break. It's going to be 1 minute. I'll be right back. Okay, give me a second. Okay, I'm back. Ooh. Okay, so where were we? Where were we? Okay, so we got this, and the next one I want to do is I want to evaluate the curve. So we can probably evaluate this same curve, right? Evaluate curve. So we take the curve, and then we evaluate that curve at a certain parameter. So I'm going to write here, for example, yes. So this is going to be the parameter, and I'm going to copy this, and it's going to give me the point, the tangent, and the angle. So I'm going to now C# script component, and I'm going to take C. I'm going to take C. Can you guys see me? Can you guys hear me? All right. Yes. All right, C, and then lowercase t. This is a curve. This is, and then we want P, T, and A. The point, the tangent, is that? Yes, the tangent and the angle. We probably want that here, and we also want an out component, an out panel, and this, and this, and this. Okay, the parameter, and we're going to take the curve here. Okay. All right, looking good. Now, so this is also going to be super interesting, I think. Let me save this somewhere that I don't lose it. Okay, good. Okay, let's get to this. Let's get to this. The next component we're going to do is actually super interesting because we're going to take the same curve that we just generated and we're going to evaluate it. Evaluate it in Grasshopper terms means using a parameter value and then figuring out all the information that we can at that parameter value. This is a concept that we're going to explore now for curves, and we will explore in this video as well, also for surfaces, because evaluating geometrical entities, NURBS, geometry is a very interesting thing. It's something that we do very often to find properties of the curve, properties of the surface at that particular parameter. And I would like to remind you again that the parameter is a numerical value that defines where in the internal domain of that curve you are situating yourself. Again, you can think of this as not an Euclidean distance, but somehow a relative distance along the curve, which also can vary in density and speed. It's a concept that takes a little bit of time to grasp. But again, you can check my Intro to Computational Design lectures if you want to learn more about this. So what I've done here is I have placed the evaluate curve component and I have plugged it in to the curve that we just created before. And I have replicated that component with C# script component. And I would like to remind you that we need to right click on the input and set that the type needs to be of the type curve. So what is curve? Curve is here. And then T, which is going to be a number, needs to be of the type double because the parameter can have and should have a decimal part. Okay. Now, the outputs that this component is going to give me are going to be the point, the actual point along that curve that corresponds to this parameter. Then it's going to give me t, which is the tangent vector at that point. And it's going to give me also this thing called the angle between the incoming and the outgoing curve. We're not going to do that. This component, this output, what it does is if a curve has a kink, so if the parameter sets you exactly at an angle where the curve is not continuous, then it's going to give you the angle between the two vectors that are tangent from the two ends at which this kink is itself. So that's an operation that is a little more involved that I would like to get on right now. So I'm not going to replicate that for this component. So let's get started. The first thing that we need to do is we need to find the point at the parameter. And again, if I don't really know how to do that, the best way to find out is by going to the RhinoCommon documentation. So I'm going to go back here to curve. You see that curve has a lot of things. For you guys for homework, you have to like sit down and look at the curve class and look at everything that you can do. That is going to be my homework for you today. But I know that if I try to find here on the curve class, if I try to find point at, you can see that I can get the point at the start and the point at the end, but I want to get the point at a particular parameter, so I'm going to keep looking at, and you can see that point at evaluates the point at a curve parameter. I think this is probably what I want to do. And yes, as you can see, the point at method, which is not static, it belongs to an instance of an object, so a particular curve, given a t-value that corresponds to the parameter, so this number, which is where we are inside of the domain of the curve, and then it returns a point 3D object. So it gives me an actual point object. So very simple. This is the one that we're going to use. So here I'm going to go to, and I'm going to say point 3D, P is going to be on the curve, so C, the curve that I want to evaluate, dot point at, and as an input, I'm going to give it the parameter, which is t as an input. And then the outputs are going to be here, are going to be this one. I'm going to click here. You can see that indeed, as I do that, I'm going to turn this off. As I do that, my 2 points are the same. And if I go you can see that indeed I can find a point along that curve. Something interesting happens here, which is that if I go over a particular value, then this component goes orange and it tells me that the parameter is outside of the curve domain. The result might be unpredictable. And which value is that? Which value do you guys think is going to be? Well, I'm going to respond right away. The value over which the component fails is the value of 12.990, because at that point, when I'm outside of the domain of the curve, I'm not inside of the curve anymore. So because the curve is a NURBS curve and is defined by a polynomial, I can still interpolate in that polynomial outside of the domain, but the results are not what I may want from the curve. So we will, in a second, implement this warning sign so that we can tell the user if they're doing something that is correct or is not correct. But for us, we still get the same result. So that's fine. We will get to that in a second, okay? Also, a quick reminder, the fact that this curve starts at domain 0 is almost a coincidence. It doesn't really necessarily, curves don't necessarily always start with the domain. They don't always go from 0 to whatever number, okay? Just a reminder. Now, what is the next thing that I would like to find? I would like to find the tangent at that point. So is there such a thing in the curve class? Well, probably so. I searched for tangent, and you can see that I can evaluate the unit tangent vector at a curve parameter. So similarly, there's a function that for a curve, we can pass the parameter value and we get a vector 3D object. So very similar as well. So we can say vector 3D tangent is going to be c dot tangent at parameter t. And then here, we can output that vector. If I click here, I get the same value for both. And so we're good for this, okay? As I said, I'm not going to implement the angle because it's a little involved, and I'd rather cover other things that I find more fundamental. Now, what I would like to cover is adding this small UI notice to warn the user that is asking for a point that is asking for a parameter that is not inside the domain of that curve. That is actually very easy to do, but it also means that we're going to have to work with intervals, which I find interesting. So let's do that. What I'm going to do is, before I do any operation, so before I calculate anything, I'm going to do a check. And that check is going to be whether if the value of t is inside the domain of the curve. So for that, I'm going to first take the domain of the curve. So that's going to be, can you give me the domain? All right. And then there has to be something like domain dot includes parameter. So you can see this, that the domain, yeah. So I'm going to create a variable called boolean is inside domain, and this is going to be equal to domain dot includes parameter. So what this function gives me is I can give it a value, and it tells me whether if that value is inside of this interval. So, and the return is a boolean, it's a yes or no. So what I can do is I can just pass in here the value of t, okay? And then I can make a check, and I can say if is inside domain, if this equals false, or a shortcut for this is if not inside domain equals true, whatever you fancy. Then here I'm going to write that warning message, but I'm not going to stop execution of the component, as opposed to some other times when we've done in the past that, because we still can find data about it. It's just that we want to warn the user that like maybe the results are not what he will expect. So I'm going to say component dot add runtime message. The level is going to be a warning, and then outside domain, you know. But I'm not going to, some other times, if the error is critical, what I would have done is I would have stopped the execution of this component, but I'm not going to do this because I still want to output the information. Okay, so as I do that, you can see that now I get the error message as well. And whenever I go below 12.90, then I am good. Okay, wonderful. So I think with this, this can be I think we're good to go. So I think we're ready for the next component, which I believe I'm going to do. I'm going to take this curve and I'm going to divide it in a bunch of points. Let's do that. Cool. All right, more stuff. Things are going well. Chat, my screen, my recording, my audio is working well. Do I have batteries? Yeah, I'm good with batteries. Okay. All right, are you guys thinking about which components would you like me to implement by the end of the stream? Keep thinking, all right? And also, quick reminder, we're moving. I'm gonna keep doing this over the course of the stream. We're moving to a new channel, so I'm just gonna post here the link of the new channel, all right? And so that you guys can start migrating and subscribing to the new one, okay? Karan is asking why I used a Boolean value here. Well, that is true. I could have shortcut this and write something like if not inside domain, and then just don't use this. I just like doing this for the sake of education, for the sake of showing you guys like really a breakdown of all the single steps. When I teach, I don't really like taking shortcuts because I think they can be confusing. So that's why I wanted to be very specific that dom.includes parameters returns a value of true or false, and then I can use that value of true or false to make decisions down the road. Does that make sense, Karan? Okay. While you hear me, and then I'm going to start writing the curve divide example. So divide curve. I'm going to take this. I'm going to take the curve here. I'm going to divide it by a number of segments. That's going to be an integer, and k is going to be whether if I should split the segments at the kinks or not. What does that mean, actually? I don't know. Maybe we can find that throughout as we go. I'm gonna put it here, but I'm not sure what that is really. And then C# script. I'm going to add here C N K B, then another T, and then T. I'm going to plug the curve in here, the number of divisions, the split kinks, blah blah blah, and I am going to put some panels in here. I'm going to write some panels in here. Panels. So this is the list of points. Okay, and I'm just going to copy it here. This is the tangents. Is that correct? The tangents, and are going to be the parameters, which is super interesting because the component also gives me where along the domain those division points are, which is actually something that we will need to calculate first. And then it's funny, we will need to calculate that first in order to get the points. I'll show you in a second. Okay. All right. I'm going to do some. I have OCD, so I'm going to do like a little bit of like cleaning up and moving things around. Okay, this will make the life of those who are helping me with the files much easier. Okay, are we ready? Are you excited? Do you like this? I should not be touching my face, right? You guys always tell me, but it's kind of relaxing. I should also get some tea at some point. Decaf tea, herbal tea. Did I tell you guys I'm quitting caffeine? I've been out of caffeine for the past 2 months, since February 22nd or 23rd or something like that. It's been quite a ride. I'm not sure if I'm ready to commit to this for forever for my life, but it's been a really interesting challenge. I recommend you guys try it. Okay. I guess this is just like another of the of my attempts to be like Daniel Shipman, because he doesn't drink any caffeine at all. Uh, so it's just my subconsciousness, like, oh, you want to be like Dan Schiffman, you have to quit caffeine, right? Obviously, I'm joking. Okay. uh, no, I have not quit. I have not quit alcohol. I enjoy a beer or a glass of wine here and there, with moderation. Yes, I enjoy it. I enjoy that. Okay. So where were we? Salvador is asking, can we define the normals with the evaluate curve point? Very interesting. Very interestingly, for if you think about this, for a curve, all right, for a curve, you can define the tangent, because the tangent is unique and it is and it is in the direction at which the curve is, and it is within the differential plane of that curve as it rotates in space. But in terms of normals, a curve at any given point, it has infinite normals, because you can do the perpendicular vector to that curve at that point with infinite rotations. So what you do have indeed is a plane that is perpendicular to that curve, which I will do also today in the videos. So the concept of a normal for a curve doesn't really have a strong meaning, because there's infinite normal vectors to a curve. What makes a bit more sense is the concept of a perpendicular plane to the curve. The concept of normal is more important, for example, for surfaces, because since a surface has 2 dimensions, then there is one unique solution to the normal. All right, I will cover that a bit later today. Who was that? Salvador. Yes. Okay. All right. I'm going to turn this off as well. And let's start now. Let's get back to it. So let's get to it. We're going to take that curve that we just created, and we're going to subdivide it into, and actually this should be here. We're going to subdivide it into a list of points at equal length segments. All right. Now, what I've done is I have cleaned up a little bit of what I had before, and I have taken the curves that we created before. I have used the divide curve component, which takes the curve, which takes how many segments do I want to divide this in, and it takes a Boolean parameter of whether if I want to split the curve at the kinks. Split segments at the kinks. I'm not really sure really what this does. I may actually not even implement it because I don't know for reals what it does. But the component, the output that it gives us is a bunch of really interesting stuff. So for example, it gives us actual points along those divisions. It gives us the tangent vectors for each one of those points, and it gives us the parameter at which those points are along the curve. And I want to note something really interesting. For example, we're going to divide the curve in segments that are equal at length, but you can see very interestingly that the parameter, the distribution of the parameter, doesn't correspond to the length of the curve. It corresponds to other stuff. And we can see that very clearly because if we have divided in equal length segments, you can see that the length, the domain interval for the first part is roughly 1.25, whereas for example the difference between these 2 points is not 1.25, is roughly 1, and the difference between these two is roughly 1.5. So the distribution of the parameter is not constant along the length of a curve. This is a concept that we need to remember, but it's fine because we will use RhinoCommon to overcome all those problems. So I created my C# script component. I mimic the inputs and the outputs, and I'm going to right click on each one of the inputs to say Z must be a curve, N has to be an integer, and K has to be a Boolean value. And now I'm going to go in and I'm going to start typing in the code. Okay. Okay, I paused here because I need to think how to approach this better. And I probably have to check here, divide. This split gives me curves, so I don't want that. So divide between curves, divide by count. Yes, I think this is going to be closer to what we want. Divide the curve into a number of equal length segments. And it also gives me already the list of the division points. This point array will be filled in, and it gives me so this is really nice. The divide by count gives me the return value. It gives me an array of the parameters at which we are dividing. So that is great because I need that as an output. And it also gives me as a byproduct, it gives me the actual points on those parameters, which I thought I was going to have to do a for loop over these parameters and say curve.point at this parameter to find all the points, but it turns out that it just gives me that. So that's pretty good. So we're just going to use this off the top of my head. Off the top, we're going to use this method right away because it's going to give us a lot of bang for our buck. So let's get to it. As usual, before we start typing any code, I would like to plan what I'm going to do. And since I never forget, I don't have I don't know what you guys think, but I don't have all these things in my brain. I always have to look things up. So getting used to reading the documentation is a really good practice. So I went ahead and I went to curve, and I just found on the page, I typed divide, and then what I did is that I found that there are a bunch of methods in the curve class that divide a curve by a lot of different parameters. So I can divide as a contour, I can divide by count, which divides the curve into a number of equal length segments. I think this is what I will want. And I also have divide by length, which tells me which divides the curve into specific length components. I think that's probably what's hiding under here. You see, divide a curve into segments with a preset length. So if I wanted to implement this component, I would probably need that other function. But I think for this one, because I want equal length, and I want the number of segments, I think this is the ones that I'm going to need here. So yeah, so I'm going to click on this one, which is, which you can see that the method returns an array of doubles. And if I look at the documentation, it tells me that this is an array that contains all the parameters that where those points, those subdivision points are. This is really interesting because I will need that as part of my output, lowercase t. The other thing that is really interesting is that as a byproduct of this method, it also gives me an array of point 3D objects, which is what I also want as part of the output. The only thing that I need to keep in mind is that this is not the return value of the function. This is what's called, I forget the technical name of this, but this is something like the like an output by reference or something like that. I forget. If you guys can look that up and tell me. But basically what this means is that I need to create first an empty variable that I have to pass to the function so that the function places in that empty variable those points that it has calculated. Okay, it's a strange thing, but this is a very useful technique when you want to have a function that returns several different things, not just an array of stuff or etc. etc. So let me implement this. So what I'm going to do is I'm going to double click here. I'm going to zoom a little bit, and then what I'm going to do is I'm going to say I'm going to define as we saw before. I'm going to define a variable which is called parameters. T values. Params is a reserved keyword in C#. I'm going to create an array where I'm going to store my t values. And then what I'm going to do is I'm going to, on the curve that has been given to me, I'm going to find the divide by count method. I'm going to put open parentheses. For a segment count, I'm going to say n. So that's the number of segments that I want. And whether if it includes the ends or not, I think the component does include the ends. So I'm going to say true to this. Now the outputs, because what I just calculated was the t values, the parameter. So I'm going to do lowercase t is going to be equal to t values. I'm going to output this, and you can see that here my t output is already spitting out these values of where those points are along the curve, which is one of the outputs that I want. So that's good. Then, but I have not yet implemented creating those points. Okay, so if you remember, as I said, this is it's an optional thing because we have two overloads: the one that takes the number of elements and the boolean, which is what I just used, and the one which also takes in an array of points and returns that array of points populated with the division points. So in order to do that, the first thing I need to do is I need to first create an empty array of points. And I don't have to initialize it. I don't have to put any points in there. It's just a container. It's an empty bucket. And then what I want to do here is I want to say, I'm going to use the out keyword, and I'm going to give this method the empty PTS array that I just created. What this method will do is it will crunch its numbers, and then it will, on this empty array, it will populate it with the values that I needed. So here, so if I output PTS as part of my outputs, we can probably see that I am getting now here, I'm getting all those points that the methods had generated. Okay. Awesome. And I think the last thing we need to implement is figuring out how to find what the vectors at what the tangent vectors at those points are. So that's going to be, that's all. I think that's going to be also pretty easy. So let's get to it. This should be just as easy as a for loop, going over all the parameters and then finding the vector, the tangent vector at that parameter, right? Yeah, I don't even know why I paused. I'm like my I have my throat is very dry today. I don't know why. I don't know if it's the weather or what is it. Anyway, okay, let's get back to it. You can declare out variable in the method argument list. That is true. That is true. So what Hari Prasad is pointing out is that there is a shortcut to what I just did, which is instead of declaring the variable before, so instead of doing this, what I can do is like I can declare it within the out argument. So I can say here, I'm going to create on the fly, I'm going to create a new point3D array. The only problem is that maybe this version of C# doesn't accept that, but definitely more modern versions of C# do accept this kind of syntax. But at the same time, as I said before, when I teach, I don't really like taking those shortcuts because I like making sure that people have a clear idea of what we're doing. So for the time being, I'm going to leave it like this. All right. Okay, so where were we? Where were we? We were about to do tangent vectors. Exactly. C#. So the C# compiler here in Grasshopper is not up to the latest standards because it needs to deal with a lot of compatibility issues. So I don't think this accepts that kind of syntax. All right. I think this is going to be just as easy as writing a for loop where we go over each one of those parameter values that we already computed, and then we ask the curve to give us the tangent vector at that parameter, and then we just save that. We store that as a list that we output somewhere on the component. So let me create a list of vector. What's happening with my fingers today? Vector 3D objects like tangents, for example, which is going to be a new list of vector 3D objects. Nice. Now the next thing I'm going to do with a for loop, I'm going to iterate over all the t values, and then for each one of those, I'm going to say double t. For example, I can't use lowercase t because parameter is going to be t values dot I, and then curve dot tangent at, then parameter, and this is going to return a vector 3D object. So that's going to be tangent, which I'm going to store here, and then tangents, I'm going to add that vector that I just created to the list of tangents. So t tangents, and I'm going to output this, and it looks like this is working. So yeah, I think I didn't explain this correctly. What I did was with a for loop, I went over all the t values, all the parameter values. I cherry picked each one of them, turned it into a variable. Then to the curve, I asked for the value of the tangent at this particular parameter, which became this vector 3D. Then I added to the tangents list, and therefore giving me this list of vectors. And I think this should be, yeah, I think it works. They both work well. Great. So this is done. Woohoo! So now we can subdivide a curve into equally spaced points and find a lot of information about those points. I feel like the next thing we could do is we could do something similar to this one, but instead of just points, we can find the perpendicular vectors to the perpendicular planes to that curve. How does that sound? Okay, is that what we're doing? Did I make a false promise? Let me double check my notes. Yes. There you go. Okay, so how's everybody holding on? Hmm? Okay. 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 Mm-mm-mm. Um. All right. I think I zone out a little bit. Okay. Oh, so I need to actually implement this first. So perpendicular frames. Yes. So we're gonna take the curve here and what is it here? Number of segments and align the frames. Yep. So number of segments, align the frames. Nice. It's okay. Bueno. It's funny how I say something and it takes like 30 seconds to reach you guys. It's kind of weird. I once I once gave a lecture. It was actually in Brazil. For those of you who are there in Novo Hamburgo, in the University Novo Hamburgo, I gave a lecture, and I gave the lecture in English, but there was simultaneous translation. So there was like a box with people in the back end, and they were simultaneously translating what I was saying from English into Portuguese. It's been the only time I've given a lecture live where there was live translation, and it was so strange because I would make a joke because half the audience was listening to me and the other half was using the translation. So I would make a joke, and half the people would laugh, and then it would take 10 seconds or 5 seconds for the other half to laugh, and so it was a very strange, it was a very strange thing. Uh, yeah, that was a long time ago. When was that? 2013. Uh, with my friends from URGIS, from the Universidad Federal de Rio Grande do Sul, Mauricio, Julia. Um, uh, I had an amazing time there. I have to say, people were so nice, so warm, and so welcoming. Um, okay, so where was I? I got distracted. Sorry. Um, um, did I copy this? Oh yeah. What? Oh, okay. Um, mm, and then I'm going to paste this here. Is there sound problems? Reverberation? Hmm? Okay, so I'm gonna turn these components off. I want to see the curve here. Ba, ba, ba. What is this? Align frames. Okay. So, as I said, get perpendicular frames, a collection of strictly increasing curve parameters to place perpendicular frames on. An array of perpendicular frames on success or null on failure. Okay, I'm not sure how we're going to implement the align frames. I don't know if we're going to get them aligned or not. We may not get to do this here today. I don't know. Yes, Rodolfo. Rodolfo is pointing out that Long Nguyen is he says that the out parameter is a way of returning like many different things as part of a function. This is in line of what I want to express as well. One method, a function can only return one type of thing, like an array of numbers. But if you want to return different types of things, then the out component is the out parameter is a really good way of doing that. Uh, um, I was actually texting with him yesterday. I think I cannot. Well, he may have news soon. I just cannot disclose. Yeah, obviously I should not disclose. But just follow him on social media. He might be making some announcements sometime soon. I want to say hi to him from here, actually. Okay. Whoop, whoop, whoop. Okay, I I got distracted again. What were we doing? Perpendicular frames. Yeah, you guys get me talking. Perpendicular frames. Okay. Let's get to it. So I have spent some time in the backend going over taking the curves that we generated at the beginning and then implementing here the vanilla perpendicular frames. This component takes a number of how many segments do I want to divide the curve in, and it takes a Boolean value that is called align frames. If you can see what align frames does is it forces them to keep some kind of like similar orientation among them. I am not sure right now how we could do that. Um, it may take us more time than I would like for this component, so I may not end up implementing that. We'll see how it goes. And here I have placed the C# mirror, so I need to change this to A. I forgot. And then, as usual, I have to remember to right-click here. C has to be a curve, N must be an integer, and then A has to be a Boolean. Okay, and we are ready to go. Now, I have done some research and I found that the curve has a method called get perpendicular frames, which needs an array of parameters. It needs a list of parameters. So at which points do I want to find those planes? And then it returns an array of planes. I think this method is great. So we're probably going to use this. But first, in order to use it, we need to compute those parameters. We're going to do exactly as we did before in the previous component. So you can see that double parameters, t values is going to be equal to c dot divide by count, and then this is going to be n, and this is going to be true. And this time, because I don't really need the points, what I only need is the t values, I'm not going to use the out keyword, or I'm not going to create an empty array of point3D objects, just because it's going to calculate more things that I need. So I don't need that overhead here. And what I'm going to do now is I'm going to create, as I said, plane, that's going to be planes, and this is going to be c.get curve.get perpendicular frames, and I'm going to pass the list of t values. When it says I enumerable, this is just that what that technically means is that that it can take anything that implements the enumerable interface, and that is we're not going to get into that, but basically, long story short, what that means is that it can take anything that can be iterated through, which includes arrays but also includes lists. Okay, so that's what I enumerable basically means. So I'm going to do that, and then, as I said, f is going to be the outputs, f is going to be the planes, and then t is going to be the t values. Is that correct? I can see that I get the planes, I get the parameter values. The only thing is that, as you can see, it looks like my component is by default aligning all those planes, whereas the other one needs to specifically you need to tell it to align those planes. I'm not sure exactly why that is, but you know what? I'm going to take a pause and I'm going to do some research and I'm going to get back to you, okay? All right, I think this has to be something as simple as if we say true, then the component is probably just like finding, if we're not aligning, then we're probably just finding the points at the curve and using the tangent to create a plane from that tangent. And if we're using false, and if we are aligning, if we're using true, then it's probably just using that method. Let me do like a really quick test if that is correct. So say yes. So I'm going to copy this here so that I don't lose it. I'm going to, yeah. So what if I do the following? What if I do this? What if I do, I'm just going to create these two variables here, and then if A is true, then we're going to compute them in a different way than if it's false, in which case we will use the technique that, no, if they have to align them, then use the technique that I just explained. And otherwise, I mean, well, this is going to be, so otherwise, just point 3D points, and then t-values is going to be equal to this, but we're also generating the points because we will need the center, PTS. We also need the center, and then with a for loop, we're going to use I'm just trying something out here. I will go back and explain what I'm doing in a second. Don't freak out. And then I is going to be less than the length of t values. And then tangents. Well, I don't actually need this really. I can just create the planes right away. So planes is going to be a new array, with the size of t values. Yeah, and then vector 3D. The tangent is going to be equal at tangent at that point. So t values I, and then planes at the position I is just a new plane with the origin. So PTS I, and I can do a plane with a center and a vector, right? Yes. So PTS I, and then that vector. Is that correct? Expected line 66. So if this is false, so these are not aligned, and these are also not aligned, right? Okay. So are they equally disaligned? Yes, they are. So they are overlapping. And the other one, and then if I now choose true, everything aligns because it's using the other method. Okay, so it looks like that was the difference between the two versions. I'm not sure why would you want the planes disaligned, honestly. I don't know if maybe this method takes more computation than the other one, but it looks like it really doesn't matter that much. I don't know, but I guess we can just explain this for the sake of completeness. Um, okay, I'm going to take this out and paste what I had before. So, okay. Okay, so how am I going to explain this? I'm going to explain this. How am I going to explain this? Well, just explaining it the way I just did it, right? Okay, let's just go with it and see how it goes. Great. I did some research and I did a quick test, and my suspicions were right. So the difference between this component, when you do not align the perpendicular frames, and therefore you can see that this one has a different alignment than this one, and this one has a different alignment than this one. The difference between not aligning them and aligning them, so now they're all aligned, is the way the component creates those perpendicular frames. Turns out that this method already gives you a set of planes that are aligned between each other. But if we don't want to align them, then basically it's just as easy as making a very similar process to what we did before, where we calculate the center. So we subdivide the curve in parameter values. We find the point. We find the tangent vector, and then we create a plane that is centered on that origin and has that perpendicular vector. And remember that for that, the solution to a plane created from an origin and a vector has infinite solutions, because that plane can be rotated any degrees around the perpendicular vector. And that's why it turns out that the vectors, the planes that we create, are not aligned with each other. It seems that this method is creating is already taking into account the orientation and is trying to match all those orientations, which is nice. But I'm just going to implement what I just said, just for the sake of completeness and to give another example of how things can be focused. Okay, so what I'm going to do first is I'm going to declare that I'm going to do some resorting. So I'm going to declare that my component I need to end up calculating both an array and an array of parameter values and an array of plane values, because that's what I want to output. All right, and then if the user told me that I need to align them, then I will calculate those t values and those plane values in a different way than if the user told me not to align them. And we already had the solution for alignment, which was this one. So I can paste this here. The only thing that I need to remember is that because I declared t values before, now I don't need to declare anymore. I just need to populate it with values. Actually, sorry, this is not correct. This is for alignment. So if we want to align them, then this is the code that we need to use. And if I run this, this works. So true, false. Oh, I have okay, I'm getting an error. I think the error is because I haven't really filled in here. Anyway, so let me continue with this. And now what I'm going to do is, if I don't want to align them, then it's just as easy as I need to figure out the parameter values for those divisions. I need to figure out the points at those parameter values. I need to figure out the vectors at those parameter values. And I need to create a plane that is centered on that origin point at the subdivision, and with that normal equal to the tangent of the curve. So I can do that very simply. I can say first I'm going to copy this, but now I also want the points at this subdivision. So I can say out PTS, and then before that I can create a point3D array called PTS, just like we did before. So now I have all those points. Now what I'm going to do is I'm going to iterate over this. This is going to be equal to t values dot length, and because for each one of these parameters and each one of these points, I'm going to compute the perpendicular vector, so the tangent vector. So this is going to be equal to c dot tangent at and t values. So t values square brackets I, so each one of the parameter values, and then I'm going to create a plane called PL, which is going to be a new plane which uses an origin and a normal. For the origin, I'm going to take the value of the points at the I location, so each one of those points, and then here I'm going to take the normal, the tangent that I just computed. And then in planes at the position I, I'm going to store that new plane that I just created. Let me see if that works. Still doesn't work. Where is this? Okay. Hold on a second. Yeah, what am I doing? What am I doing that I wasn't? Planes. 70 unassigned. Oh, I need to construct. Yeah, I need to set the length of the. Yes. All right. Okay, sorry. Yeah, I forgot because here I declare the planes array, but I didn't say what size it has to have. I don't need this for get perpendicular, because this method takes care of creating a new plane array and assigning it to here. But here I need to create an empty array of planes before I start populating it with values. So that's why I need to say plane, and then here I need to say the length. So that's going to be t values dot length, how many elements this is going to accept. And as we do that, that should be good. And you can see now that false gives me planes that all have the same non-alignment, and true are planes that all have the same alignment. They're all aligned within each other. All right, so another one is done. Another one bites the dust. Boo! Another one bites the dust. Boo! Right. And then, okay, so what are we doing next? We're gonna loft a surface along a set of curves. All right. Okay. Now, that was a lot. What else am I doing? Yes, loft surface. Okay, so I need to turn all this stuff off. I'm going to internalize these points so that I can remove them from the screen. And then what am I going to do? I'm going to create like a bunch of curves here. All right. Oop. Nope. Okay. Okay. And then I'm going to create a curve, and I'm going to pick them up in the right order, and I'm going to loft the curve, and loft options. Well, how is the video How's the video? I'm getting these messages here that my streaming connection is not great. The bitrate. Are you guys, is it choppy? The audio, the video? Is it good? Okay. The Loft options. Left options. This is going to be, no, we're not going to be able to mimic this, really. And then this is going to be O, and then the output is going to be L. Okay, this one is should be easy to do. All right, no issues. Okay, sounds good. Okay, let's do this. We're almost done. Are you guys thinking of what would you like me to, which components would you like me to replicate? I may have time for one or two, depending on how difficult you guys want it. Keep it in mind. Okay, and we're also probably going to do some Q&A as well, if you guys want to hang out and chat about life, the universe, everything. I don't know. Okay. Are we ready for this? Probably. Are we ready? Probably. Image sampler. No, we're not gonna have time for that. Pixel car. No, that is very involved, and we need to unpack a lot of stuff. Also, Grasshopper doesn't really natively have any special thing to support bitmaps, so we will need to have to use system bitmaps, which Saeed says custom attractor component. Which component is that? Is that an attractor component? Anyway, we'll talk about that. We'll talk about this by the end of when I let me finish this first, and then we can talk about that. Let's get lofting, right? Now I created three curves in Rhino. I brought them in as a parameter component here in Grasshopper, and then I fed them into a native Loft component that just gives me this nice smooth NURBS surface that passes through the three curves, that lofts through the three curves. We're going to try to mimic this. The only thing that I would like to say is that how this component works is that it takes something called loft options, and here you can specify things as whether if you want the loft to be closed, whether if you want to adjust the seams, whether if it's a tight loft, a loose loft, etc. And then what this component does is it packs all those things that you specify, and then creates an object called loft options that then gets passed into the loft. I don't think we have that possibility in C# scripting. We cannot create loft option component objects. So what I may do is I may just mimic some of these inputs here straightforward as part of the, as just like regular inputs for this component. I want to make sure that we remember that the input of curve must be a list. So because we must be able to see all the curves as a list, and that options, whenever we get to that, we will figure out what this O should be. Okay. Now let's get coding. Oh, you see, I forgot. This input reads list of objects, and no, I want this to be curved because I forgot to specify that this must be curves. This is a really common mistake. I make this all the time. I forget to specify the types. Okay, now don't remember. That's why I've been doing this consistently for all the videos. So let's get to it. But as usual, the first thing that I would like to do is I would like to go to the documentation and figure out how can we do this. So before we were exploring the curve class, but I don't think we will be able to do that anymore because probably if we're creating a surface, then lofting will be part of the surface class or the brep class. So let me just write here on the general search. Let me just create loft. What you can see here is that loft, create from loft, belongs to brep, the brep class. And there's a lot of things that this component, this is a really complex method to unpack. But long story short, the brep class, which is the class that takes care of representing a lot of surfaces combined with each other, is able to create lofts as a static method. Again, static method means that instead of calling the method on an instance of a class, on an instance of a surface, an instance of a curve, we call it directly from the main class. What this will give us is it will give us an array of breps, because there are certain situations where a loft among a list of curves will give us different surfaces, not just one. The inputs that it takes is an I enumerable. Remember, I said that this is basically anything that can be iterated through, like an array or a list of curve objects. Then, as here, and I'm not inventing this, this is all these things, you can read them here as part of the parameters. It takes a start and end point if you want to align this loft. But if you don't want, you can just say, you can use point unset to just not care about that point. Loft type will be an enum. And as I explained before, enums are just ways of giving names to integer values or to other values. So we can probably use an integer to specify if we want normal, loose, tight, straight, developable, whatever. And then whether if we want the surface to be closed or not. And this is a true and a false thing. So these are some of the parameters that are part of the loft options. So for example, here t, whether if you want tight, normal, loose, straight, etc. So what I'm going to do is I'm just going to add a t parameter here, which is going to be an integer, so that I can specify how tight or not I want the surface. And I'm going to also specify, add a CLS input here, because to specify if I want the loft to be periodic, which is also is the same, is a synonym to closed. And so this is going to be CLS, and I have already specified that this has to be a Boolean, and T, I specified that it has to be an integer. Okay, so I think we're in pretty good shape. So this is going to be super easy. Once we understand what we can use and what type of inputs, I'm actually going to copy paste this here so that we can take a look at this. Okay, it looks terrible, but the way I'm going to do this is brep, and I'm going to call this, it's going to be an array of breps, and I'm going to call this surface. I'm going to use the static way of calling this method, so brep.create from loft. All right, you can see that I have all this specifies all the inputs that I can give it. So the first one, the list of curves, is going to be C, that's coming in from my inputs. The start and end points, I don't want to care about those here. So that's why, as per the documentation, instead of giving it an actual point, I'm going to use point 3D unset. So here I'm going to specify point 3D unset and then point 3D unset. This is basically a way for Rhino to be able to, point unset is just like a point that doesn't really exist in a way, but it's Rhino's way of defining that a point is non-existent or is null, because they cannot be null because they're structs. But that's a different conversation that we don't want to have right now. Then for loft type, I'm going to start with normal, but then I will link that to the input at some point. And then for whether if it's closed or not, I'm going to use the value of CLS, which is the input that we just got. And then here, L is going to be the loft. Let's see if this is working correctly. So I do this. I'm going to paste here. I'm going to turn this off, and as you can see, this is already giving me the surface that I want. So toggle, Boolean toggle, and I can like make it, I can close it, I can wrap it or not with the CLS component. But now let's explore the Boolean, the Loft type. The Loft type is going to be an integer, remember, which let me bring this again. Options Loft, as we have here, is going to be an integer. 0 is normal, 1 is loose, 2 is tight, 3 is straight, 5 is uniform, just like we had it here. Okay, and so I'm going to plug this in here, and what I'm going to do is just simply before I get into this, I'm going to define a variable of the type Loft type, which remember is an enum. L type is going to be equal to Loft type t. What I'm doing here is I'm taking the integer. Remember the problem we had before? We couldn't really use an integer to define an enum. So what I'm using is I'm taking the integer, this integer value, and I'm casting it to an object of the type Loft type. And then C# takes care of figuring out if it can convert this integer to something that feels like Loft type. And then I'm going to use this here. And then the Loft, you can see, oh, this is terrible. This should be 5 or 6 stops. So 0 is normal, 1 is tight or something, I forget, loose, 2 is tight, 3 is straight, 4 is non-existent, and 5 is uniform. Okay, so there you go. So that was pretty easy, actually. The only complicated thing was finding in the documentation create from Loft and kind of breaking down exactly what this whole thing means. But aside from that, it was pretty straightforward. Good. And the last but not least, we're going to evaluate a surface. That is also a really good exercise, just like we did before here. We had the curve, and then we evaluated it. We found information about that. We're going to do the same thing with the surface. Okay. I'm going to take a second. Okay, I'll be right back. Give me a minute. All right. Andres Obregon. You have a question about checking for nulls. We don't have none in C#. That is the Python way. In C#, none is called null. And you can check for things, whether if they're equal or not to null, just like you do in Python. So you can So you can do that. The only thing is that C# has two types of classes. Objects that are structs cannot be null. So you cannot do that. You cannot do that with structs. So for example, point3D and vector3D are structs. So you cannot you cannot do nulls, and that's the reason behind the whole point3D unset. Okay, so now let's evaluate the surface. Whoa, that is a lot of stuff. And then UV. Okay, so let's create. Let's construct a point, and then let's do, for example, X, and let's do, for example, X and Y. So that, and so we get the point, we get the normal, we get the U direction, the V direction, and the perpendicular frame. That's quite doable. Okay, so let's do C#, and this is going to be S, and this is going to be UV, and outputs are going to be P, and then these are going to be U, V, and then I need the normal here. I need the normal, and then I need F. Okay. And I'm going to plug in a panel here. Point, here and here. Okay. And then point here, 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 and here, because we have nothing yet. The surface, the point. Okay. All right. Well, let's get through this because I have meetings all afternoon long. So let's do this. Cool. And I think I may wrap up this video. Maybe I do one or two more components as a bonus, but I think I want to wrap up what I wanted to say today by doing a very similar exercise to what we did before, which is we created a curve by using some points and interpolated, and then we evaluated that curve. We found information about that curve along the parameter. So I'm going to replicate the exact same concept, but in 2 dimensions. Here we created a loft, which is basically a surface that went through a list of curves, very similar to a curve that goes through a list of points. And then now what we're going to do is we're going to evaluate that surface at a particular location in the UV domain. And the UV domain of that surface is just a parameter that has 2 values, one in the U direction and one in the perpendicular one in the V direction. So what I've done is I have dropped here the evaluate surface component. I plugged in the loft that I created before, and then I plugged in here in the coordinates to evaluate, I plugged in a point. This point here is an Euclidean point, but what this component does for evaluation is it just takes the XY coordinate of that point and it uses those as the parameter in the U direction and the parameter in the V direction of the surface. So we don't really need a point in 3-dimensional space. What we just need is the 2 values for U and V packed into something. That's why it's taking a point, but it could take a vector or it could take anything that literally is just a list of numbers internally. I have mimicked that in C#. I have plugged in here the surface and I'm going to right click here and I'm going to right click and say that this has to be the input type of surface. And then here UV, I'm also going to right click here and say that the input has to be a point 3D. Okay. As I do that, I'm going to open my code editor. But before we do any coding, I would like to go to the surface class and take a look at what methods might be useful for me to find a point, a normal, a frame, and such. So for example, I'm going to search here for a surface, see if I can get to the surface class. Nerves surface methods and nerves surface class. So it turns out that yes, there is a lot of stuff here. This is the nerve surface class, and it gives me a lot of properties of that class. But it also gives me a lot of methods. So I can find the closest point to that surface. I can create a curve on top of that surface. I can create surfaces from points. I can find the curvature. I can find the degree. I can find the domain. I can evaluate a surface mathematics. There's a lot of things that you can do. I can use frame add, so this would probably be very useful. I can find the frame at a particular U and B, and it gives me the plane. I can probably, what is evaluate? What is this giving me? Here it gives me, for example, a point at a particular, given UV parameters, it gives me a point at a particular location, and it gives me two vectors, which are the derivatives. So basically, that is a way of saying those are the two tangents of that surface at that point. That could be really interesting. So that's probably what I would like to use. So I think between evaluate and frame add, I'm gonna have a good time here. So let's try to do that. So the first thing is, for example, what is P? Now let's start with something simple. Let's start with F. So F was the frame, and here we have frame add, which gives me a plane. So that's going to be simple to implement. So what I'm going to do is I'm going to start with frame is going to be equal to surface frame add, and then for the U and V, oh, I'm not using this. Wait. I'm not using this method correctly. Let me backtrack and let me look back at the method. How the method works is that it doesn't return the plane. It returns a boolean that tells me whether if the method was successful at finding that frame or not. This is a very common pattern, because sometimes operations fail. So you want to have like some way of knowing if this operation was successful or not. I'm going to, so that you can read here. And the way it gives me the actual plane is by using this syntax that we saw before, using the out keyword to reference into a plane that needs to be output by the method. So I'm going to do that. Plane P frame. I'm going to create it beforehand. And then what I'm going to do is here, I'm going to say success. I'm going to say frame successful. And then I'm going to call the frame add method of surface. As you can see here, it returns a boolean value. The UV is going to be from the point that I just input. U is going to be the x coordinate, and from the point that I used as an input, V is going to be the y coordinate. And last, I'm going to use the plane object that I just created to store the result of this computation. So I'm going to use now F equals frame. Let's see if this works. Does this work? It does work, but it's giving me a frame that is not exactly the one that the component is giving me. That's interesting. I am not sure why that's the case. I may need to take a look at that down the road. But let's continue. Let's now use the evaluate method to find information about this method, about this surface at this UV. Oh, it's been a long morning, huh? Now, so I'm going to follow a very similar. So evaluate is giving me a point and it's giving me an array of vectors. So I'm going to define those two beforehand. Point 3D point, and then vector 3D array derivatives, and then Boolean success, evaluate success is going to be equal to s dot evaluate frame, evaluate surface, and then uv.x, uv.y. Then the number of derivatives means how many times do I want to perform derivatives on this surface. But that basically means, how can I explain this? The first derivative of a curve is the slope of that curve, and if I do a second derivative, then I'm calculating the slope of the slope, and so on and so on. So long story short, I want to use the value of 1 here, I think. And then out is going to be point. I'm going to store the result of that in the point variable that I described before, that I declared before. And I'm going to store the derivatives in the vector 3D array that I declared before as well. Derivatives here. I'm going to run this and see if this works. I get no errors. That looks promising. So let's see the results. So P is going to be equal to that point that I calculated. And is that true? I am getting a different point. Well, at least this point and the point of the center, they do match. So that's good. Why am I'm not sure why I'm not getting the same values, but we'll get to that at some point. And then the derivatives, U and V are going to be those two directors. So U is probably going to be derivatives 0, and V is going to be the derivatives 1. So those are the perpendicular vectors in those two directions are U and V, which they kind of look similar to these ones, but because we're not in the exact same location for some reason, I don't know what's going on. And then what is N? N is the normal. So I'm not sure if there is a normal at. So it does seem like it computes the normal. So I think we can use that. We could also just multiply the two derivatives and do the cross product and then find the normal. That is correct, but I need to double check that. And then, so vector 3D normal is s dot normal at uvx, uvy. And as we do that, n is going to be equal to normal. And we have the normal here. Yep. So, and that is what it is. So I have noticed, so I think what we've done is correct, but I think there's something wrong about how the two components find the UV space. I think probably the evaluate surface is doing some pre-processing of these values, so that, and that's why we're getting different locations for the plane and for the point. So maybe this component is actually normalizing the domain and reparametrizing it. I am not sure about that, but I'm not going to solve this right now because it's been a long morning already. So I may just do like a small, I may just figure out later and do like a small piece next video, and then add this, and then add the solutions of why these two values are different. Okay, but this was basically evaluating a surface. All right. Okay. So I see YouTube is telling me that I'm having connection problems. Are you guys seeing the video? Is the video choppy? Is the video, is the audio choppy? Quality? How are we doing? Okay. Okay. You guys still there? I can see you. Okay. So I'm going to record. I think I'm going to. Well, let me just say. Do you have I have time. Let's do just one component. Okay. One more component. One something that you guys want to do because I have to go. I have to have lunch before my meetings, and I still have to record the introduction to the video. So suggestions. What is the one component that you would like to see implemented? I'm taking suggestions right now, and I'm going to give you 30 seconds till, because of the lag, I'm going to check my phone. Okay. It's the surface closest point component to get the UV. Clean tree. Nah, that's a little bit. So we could use surface closest point, perhaps. Vrep closest point, surface closest point. We could do this point, coordinates of the point, and distance between sample and point. This could be interesting. Surface subdivision, mass addition. Okay. I think I'm just gonna do surface closest point just because we have it already. We have the surface, and it's an interesting one. So let me just do this. So we have the surface here, and then I'm going to put in a point somewhere here, for example. I'm going to internalize that point. Okay, and I'm not going to clear values, set one point. Okay, and then this is going to be here, and C#. Okay. So this is going to be surface P. This should be P out, and this should be UV of the point, and this is the distance. Oof, well, I'm really tired today. This was intense. I don't know how you guys deal with this. This, and this, and then here, this, and this. Okay. All right. Okay, let's do this. And last but not least, requested by the audience live here on the stream right now, I'm going to do surface closest point. I think this one should be pretty straightforward. And this is a component that basically takes any point in 3D space and computes the most proximal point on the surface to this point. It gives us the point on that surface. It gives us the UV coordinates of that point on the surface, and it gives us the distance between the original point and the point that we just computed. So this should be pretty easy. If we look at surface, I think there is closest. We should be able, yeah. So there is closest point. So here you can see we have Boolean closest point, we have the test point, and it gives us the U and V parameters, which then we can use to evaluate the surface on that U and V parameter. So That should be pretty straightforward to do. As you can see, I have forgotten to set the types of my inputs. So I need to right click here on P to say that this must be a point 3D, S must be a surface, and then I'm going to go here and I'm going to say, well, let me look again at closest point. It was a Boolean, the return is a Boolean, whether if it found the point or not. Then the test point and the out is U and V. Okay, so I'm going to define U and V as the outputs that I need to find. Then I'm going to say success is going to be equal to surface dot closest point. Then the point that we want to test is P, and then out is going to be U and out is going to be V. Let's see if that works well. So for outputs and UVP, I'm going to create a new point with U, V, and 0. And let's see if this works. Oh, I got a problem somewhere. Point geometry, oh, sorry, this is point 3D. Yes. So here we got two very similar values to the original one. Again, I think we're having the same problem as we had before. I think there's something with this component maybe is reparameterizing the surface. Maybe it's not. I don't know what's going on. I need to take a look at this somehow, but it's close enough. So, and then what else? P out. Well, so now we need to find the point. So I think we used to use evaluate, and this gave us the point and the directions. So that's fine. So point 3D point and vector 3D array derivatives, and then S evaluate. So U V one derivative, then point, then derivatives, and so here P out should be the point that we just calculated. Is that correct? So there is something that is not working here. Oh, I forgot the out keywords here. Yeah, so again, the point is kind of close. It's not exactly the same for whatever reason. I need to take a look at this. And then the distance is going to be super easy. Double D is going to be point distance to the point that was coming from the input. And then as the output here, we can just do that. And because there's a slight offset here, the distance is not exactly the same either. Okay, so this looks good to me. So all right, so this was surface closest point, and with this I am wrapping up this video. We implemented a lot of vanilla Grasshopper components that have to do with geometry. We learned a little bit about reading from the RhinoCommon documentation and figuring out how to perform these operations based on the documentation. That is a very, very important thing to learn when you are writing C# scripting inside of Grasshopper, or in general when you're using somebody else's libraries. Okay, so I'm gonna stop here on this video. I might continue doing more series of this if people want it, if I find components that are interesting to have a conversation around. So if those videos are live, you will see links to the continuations here, or like a card will pop up here somewhere pointing you to continue learning. But in the meantime, stay safe, stay healthy, and code a lot, and tag me, or send me stuff if you do cool stuff with this. Okay? Thanks a lot. All right. Introduction. I need to do the introduction. Why is there a line here? I need to do the intro. The intro is going to be, what is the intro going to be? The intro is going to be just explaining what we're doing today here, showing a little bit of this, and ended up with this surface, I guess. All right. I'm gonna do a little bit of Q&A when as soon as I finish this. If you guys want to stick around, like 10 minutes. All right. Hi, and welcome to the second iteration of the series of videos that we're calling Grasshopper Sharp or GH Sharp, because what we're doing in these videos is we're taking standard vanilla Grasshopper components, the ones that come with Grasshopper out of the box, and then we are trying to implement and mimic those functionalities with C# scripting so that we learn a little bit more of how to write our own implementations, but we also learn how to use RhinoCommon and how these operations that are described by the vanilla components, are actually implemented within. In this second part, I'm going to tap a little bit on more advanced topics. We're going to be working a lot with geometry, so we're going to be doing curves and we're going to be doing surfaces. So what you're seeing here is, for example, a manual implementation of a lofting surface through a component, through a list of curves, and then evaluating the surface to find things such as the point at a particular UV coordinate, the normal, the frame, etc. We're going to learn how to read the RhinoCommon documentation, and we're going to learn what kinds of inputs and outputs and the methods in RhinoCommon take, and how we can write them inside of these components. So this is going to be beginner/medium level, but if you have any questions, the code will be on the description here and in our GitHub repo, and you can always reach out to the community if you have further questions about this. So let's get busy and let's start crunching down some components, okay? All right, and that's it. Woo! Whoa, I'm really tired today. I don't know what have you guys done to me? Huh? Oof, oof. Well, if I'm tired, I don't know. I don't know how you guys are going to feel about like all the stuff that I just dumped on you right now. Okay. All right. I'm gonna open it up to some Q&A. Aman is asking whether if I can guide folks to some resources on custom code for Delaunay triangulation algorithm. That is actually a really interesting topic. I cannot point you to a good reference, but actually, like, I would be interested in perhaps giving it a try. I've never implemented Delaunay from scratch, but I could take a look. I don't think it's that hard. I think doing it fast in an optimized way is not straightforward, but I could take a look and then maybe we can just do it here as part of the stream. Actually, that's a good idea. I am going to write it down as suggestions. This could be a geometry gem. Delaunay from scratch. That could be a good topic. But no, I don't. Off the top of my head, I don't really know a good resource. Sorry. Vacaris says that I am a machine. I'm going to take that as a compliment because I think that's what I mean. That's what you mean. But I would like to think that I'm still human a little bit. Okay, I spend a lot of time with robots and neural networks, and the more time I spend with those, the more I appreciate my flesh and my emotions and my feelings. So I'm conflicted. I want to be a machine, but I also want to be human. So I don't know where I stand on that one. Salvador, take a loft type and have different types from the surface. I'm not sure that's the case. I think there's something with the UV coordinates and its interpolation on the surface. I need to take a look at that, but I can probably shoot like a small clip next time and add it as like a supplement, like a bonus video, to figure out what went wrong. Thank you, Fagan, for your words, and Kaveh. Saeed, C sharp makes me hungry. It makes me hungry. I'm very hungry right now. As you can see, from my YouTube, I'm learning a lot of cooking in this quarantine. I like cooking a lot. It relaxes me in the evening. So maybe I can cook for you guys at some point in the future. Maybe I could start a cooking channel. I do. I'm getting really good at paella. I really need to share that with the world at some point. Another question, Andres Oregon. Yes, the code that we have done for Game of Life, for example, and everything that we have done before is publicly available. Um, do I have internet? Do I have connection? It's publicly available on our GitHub repo. So this is here. We have a repo here, and all the files of all the videos that we're going to shoot. We haven't published the Game of Life video yet, but the code is in that repo already, so you can check it out. And it's in this repo here. So we have a parametric camp GitHub organization, and there's a project called tutorial files, and here you can see the memorial exercise, the Game of Life. Here is GH sharp. We're going to be posting all these code samples here as we make them. So you can go there and you can download now. The video will be published next week, but you can download that right now here. Also, a gentle reminder again: please subscribe to the Parametric Camp channel so that we can start transitioning there. I'm going to post this again on the on the chat because I'm a pain in the ass. But yes, remember to subscribe so that we can start transitioning and get out of my YouTube account. What could be a good resource to understand geometries better? Like how planes actually work. There are a lot of books about geometry, abstract geometry. There are some books about computational geometry. I like Woodbury's Elements of Parametric Design book. I like Kyle Steinfeld's and Joey Koh book on, I forget the name, geometry something something. But if you go to my playlist, my Harvard playlist, there are here in the course introduction, by the end of the video, I talk about like a bunch of books and a bunch of tutorials that you can check. And also, if you want to learn more about computational geometry, this playlist is also, I think it's good, but I made it, so I'm also biased, obviously, you know. So you may wanna check that out. GH Grasshopper tutorials. Thank you, Vakaris. Thank you, Sujai. The red color also makes you hungry. Vakaris asks if I have interest in 3D printing. I do. I have 3D printed a lot, but I am not very interested in the actual print or the machines. I'm more interested in like how to go from three-dimensional geometry, so meshes, shapes, blah, 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 and all the geometry processing, all the slicing and all the processing, how to translate that to G-code. That is the part that I'm really, really interested in. And I'm also super interested in what I call non-standard 3D printing. So instead of taking a model and slicing it and making like a solid object, like writing G-code from scratch and making things that are not solid but are like lines of plastic, PLA crossing, and like it's almost like stitching in 3D. I actually have one of my exercises in my Harvard course is to write a G-code compiler from scratch so that you can 3D print anything in 3D. So that's the part that I really like about 3D printing. I actually I published where is that? Gamingcat.org. I published a paper with some students of mine recently about let's see if I show up here. I published a paper about, we made a really cool project where we were using an industrial robotic arm to 3D print clay in 3D. This is not the one. This one, responsive spatial print. We made this thing where we were 3D printing with an industrial robot, something that was porous, so it was like a three-dimensional structure. So we could reach much greater volume with less material. And there was a challenge because it was clay, so it was very soft and squishy, and it deformed. So we created this method, this feedback loop method, where we could 3D print and then we could read the deformation and 3D print again. This is not part of this paper, but we're actually working on a new paper. We made like a really large prototype that we will be printing, that we will be showing at some point. It's like a, and I also did with some of my colleagues at the research group at the GSD. We also made this really cool pavilion in Spain, which was fabricated with clay bricks. Each one of them also was parametrically designed, and we also wrote the compiler, and each one of the bricks had the shape to adapt to the pavilion, etc. We couldn't really finish the full thing because we were out of budget and time, but we printed like a third of the bricks that were going to go into the pavilion. So that was a really interesting project. This was 2017, I believe. You can check these papers on the CuminCAD database. If you just Google my name, Garcia del Castillo, I should pop up, hopefully. All right. Kevin is asking if I'm... Hey, Kevin! How are you doing, man? Where are you calling from? Are you in Europe or in Switzerland? Am I taking part of any conference this year? I was going to teach a workshop at Fabricate and another one in Smart Geometry, but they got canceled. They got postponed. I was actually going to teach that. I was going to teach a workshop with my friends from University of Las Vegas, from Boston Dynamics, and from Tesla. And we were going to bring like the creepy Boston Dynamics, like the dog robots that walk around, and we were going to make them build something. It was going to be super cool, but we are not doing that right now. I might take part of the Digital Futures Conference, which is happening in July, and it's going to be fully online. I may do that, and I might do Acadia in the fall if we're working on a paper there. I may do that if we get accepted to the conference. So hopefully I will get to see some of you in those conferences, if we ever go to physical conferences anymore, right? Okay, so all right, somebody's asking to links to the papers. All right, I'm just gonna copy paste here on the link to searching, and this is, I'm going to paste here the 3D printed pavilion. I'm going to print here the 3D print and the responsive spatial print. But you can check other papers. If you go to CuminCAD, you can check like a bunch of papers that I've written either myself or together with my research colleagues here at Harvard. I belong to what's called the Material Processes and Systems Research Group at the Harvard Graduate School of Design, and we do a lot of intersections and digital fabrication, and we've done a lot of work in clay, for example. So we have a really good team, and we're doing like what I think is interesting things. So you can check them out here if you want. All right, wonderful. I think with this, I'm gonna call it a day because I'm super tired and I need to have lunch, and I have a lot of students that I need to take care of, and I have meetings, and I have things that I want to do this afternoon. So thank you very much. Stay tuned on the YouTube channel, Instagram, Twitter, etc. And I think hopefully I will start, as of next week, I will start doing 2 streams every day, one in the morning about a particular topic that we decide, GH Sharp, other things, Delaunay, whatever, And then in the afternoon, I may want to start recording like the first significant, the first long list, the first long list of videos that form a playlist. Whether if that is, let's start with regular Grasshopper or let's start with C Sharp. I want to think about this week, but hopefully we will start doing that next week. Okay. Everybody, have a great day. Thank you so much. And thank you for sticking around. And we will post the videos as soon as possible. Okay? Bye bye.